Welcome to this last talk of the LLVM toolchain dev room. My name is David Juhász. I work with software at IMSIS, and in this talk I will tell you about how we use LLVM at this company. But first, just warm up with some very basic LLVM stuff. How do you use LLVM? So if you have your software application in some high-level code and you have a target architecture where you want to run it, then you need to compile. You take LLVM. And what's happening inside LLVM is first you take a front end which can turn your application from your favorite language into LLVM assembly or IR, the intermediate representation. Then you can use the LLVM middle end to optimize this intermediate representation code. And then finally you take a backend which targets the device, the architecture where you want to run your code on. And this backend will turn the LLVM assembly into your targeted architecture assembly code or binary executable code. What this talk is about is how we want to improve the efficiency. And I will tell you efficiency in what sense. If you consider LLVM assembly and a typical target architecture, then there's a big gap. The backend needs to do typically complex translations. There's a big semantical gap. Instruction set architectures are typically not designed with respect to the compiler's intermediate representation. What we want to do at IMSIS is lifting the instruction set architecture closer to the LLVM assembly level, so reducing the gap. And then we use an LLVM backend to target this architecture. So that's what the main topic of this talk will be. But first, I would like to very briefly just talk a few words about the company itself, what we are doing. Then the IMSIS Lean processing technology, our core technology, which we utilize to be able to reduce this gap. And then, last but not least, I will also say a few words about our tailor-made instruction set for LLVM. So, IMSIS AB is a Swedish semiconductor SME. It's located in the North Stockholm area. We are working with our own proprietary processor core. We sell devices, modules, the processor IC, and in the future we plan to go to sell IP as well. The company has a history as supplier of network embedded controllers with some special features. These pictures are some of the actual applications, devices where our processor was used. But now we want to retarget our processor for the Internet of Things, as we see some good match for our values. And using LLVM is part of this retargeting. As a device, we want to provide a single controller solution for IoT applications. That's the IMSIS Embla. It's a small handful application or a device with some I/O capabilities. It can be connected directly to an LCD display and a touch panel. And the different I/O capabilities can be used with an extension board for which we have a reference design. Software-wise, which might be more interesting in this session, I would like first just to give a very high-level overview. So you can have our development device, and then you develop your application code. And we support you with an Eclipse-based integrated development environment. You can develop your application in C and C++, in which case we want to use LLVM to generate executable code. And also, we support Java execution. All right, that's about the company. But don't forget, this topic is about how to reduce the gap and have a tailor-made instruction set architecture for LLVM. So first, I tell you about the technology which we use to reduce the semantic gap. Let's revisit the software layers, the abstraction layers. So we have the IMSIS processor core, which supports an instruction set architecture. Then you have your application code again, which can be Java or assembly C, C++. And our instruction set support provides basically two instruction sets. One we call ISAJ, that's for an ISA for LLVM, and ISA ISA is for LLVM, and ISA-J is an instruction set architecture for Java. Now I won't talk more about Java. Let's focus on the LLVM stuff. Here, if you want to think about what are the main levels of abstraction, then usually you say that yes, we have a hardware. The hardware provides us the instruction set architecture, and then we have our software which runs on this instruction set architecture. But actually there is a, let's say, a forgotten layer of abstraction. Historically it was there, but nowadays it's not, it's very hidden and typically not used much. That's microcode. And actually microcode makes it possible to have a really, really tight control over what the processor does. So I would like to give you a brief idea what microcode is. So the processor has a microprogram. The microprogram is a list of micro instructions, and each micro instruction consists of fields, separate fields, and each control field has a control value which directly controls the different the behavior of the different functional units of the processor. One of the functional units is the sequence control, which then decides which micro instruction to execute next. So this is a very direct, close control over the features of the hardware. And an architecture which operated by microcode is basically an operation-oriented hardware architecture. Every step inside the processor is directly controlled by the microcode which we develop. All right, so that's how microcode works. You have some idea now, but what is it good for? There are a few things which we value in microcoding. First, as I already mentioned, we have complete and actually deterministic control over what the processor is doing. Then our hardware, the processor core, can be minimal since all the complex control logic is implemented in microcode. So there is no need for deep pipelines, we don't have cache hierarchy, out of order and speculative execution, we don't have a complex hardware state to maintain. Also, since we implement different features in the microcode with direct tight control, it means that the utilization of the actual hardware can be maximized. So we provide maximum efficiency with our hardware. Microcode also means flexibility. So we can basically implement any kind of computation in microcode, which makes our processor core a multi-purpose device. We can develop a general purpose instruction set architecture, but we can also microcode special digital signal processing features like FFT or encryption and so on. And also, since microcode is a very special kind of software which is stored in a special memory in our processor, we can overwrite the microcode, we can reconfigure the device dynamically. So that's also an important feature for the future. So if you think about the abstraction layers again, then we can match them to this hardware microcode software layers. So the processor core itself is of course hardware. And then the instruction set support, the instruction set architecture is actually not hardwired in the processor core. It's defined by microcode. And then above the microcode we have a quite thick layer of software. On the high level is the replication code, and the lowest level is the instruction set, which is implemented in microcode. And the high level and the low level software is connected by LLVM. Okay, so what it means, I just would like to point out what it means to have a microcode defined instruction set architecture. Typically, you have your application code, and then you have a compiler which turns it into your assembly code and binary executable. And that's typically hardwired into the processor. But if you think about an operation-oriented hardware architecture, that actually the microcode supports us to lift the instruction set architecture from the hardware to a higher abstraction level. So what it gives us, what the it gives us this abstraction possibility is that we can implement domain-specific operations, like I mentioned, FFT, encryption, and whatever. And it also provides us with the possibility to have a rich and balanced ISA which the compiler can target. Okay, so that's about our core technology. And then I will focus on, for a few slides, on the actual instruction set architecture which we are implementing for LLVM. So we have LLVM assembly, everyone knows that very well. And then we have our own ISA-L instruction set architecture. So first, what do I mean when I say that we lift ISA-L to match LLVM assembly? It means that we provide semantically matching instructions for basically all LLVM assembly instructions. So it means you have an addition in LLVM assembly, then you have an addition in our instruction set architecture. Of course, this is not a big thing for these basic operations. Every processor has an additional instruction, but we have the same matching, semantically matching corresponding instruction for complex operations as well. For example, like bit reverse operation, count leading zeros, or even intrinsics, floating point operations, and things like that. So we developed our own LLVM backend, which turns LLVM assembly into ISA-L. And this backend does not need to do very complicated things, actually. So it's very simple, kind of efficient, and mostly it uses general LLVM facilities. And this is thanks to the matching semantics. Also, of course, LLVM assembly code can be optimized using the LLVM middle end. And we are very happy with that because we have direct use of those general LLVM assembly level optimizations because our backend will not modify much on the semantics of the code. So we benefit directly from the optimizations. And also, since the ISA-L instructions are matching the LLVM assembly instructions, we don't need to do much more target-specific magic in the backend. And so far so good, but LLVM is based on a theoretical model which has some characteristics which makes it practically impossible to directly implement, of course. So we need to think about how to constrain ourselves to be able to implement an instruction set architecture for LLVM. First thing is operations. So LLVM assembly has instructions and intrinsic functions. As I said, we support or we provide the semantically matching operations in ISA-L, and additionally we needed to add some kind of system operations, management operations, like handling I/O, managing the execution state, and also some special data movement operations. Then the next thing is the supported value types. So LLVM assembly has virtually an unlimited number of single value types. If you think about, there are a lot of floating point types and much more possible integer types. Okay, they are typically not used, but they are there in theory. So of course we need to define a set of integer, floating point, pointer, and vector types which we support. Then registers. LLVM assembly has an unlimited number of registers, which is again impractical to try implementing. So we defined a set of register windows which we support. And of course, when talking about registers, it might be worthwhile to mention that of course there is a big difference between LLVM assembly and reality, as LLVM assembly is in SSA form, static single assignment form, which is again not practical to implement, so of course we don't support that. As for the arguments, basically each instruction has source and destination registers as arguments. I will tell you in the next slide why this is not always efficient to have, or why it is not always efficient to have only that. So we added special instruction variants to support accumulating in source registers and also to work directly with immediate values. And also the binary representation is very important for us. So LLVM assembly has the bit code as a binary form. We developed our custom dense binary coding, and I will tell you some more details about that too. All right, so optimizing operation sequences. First, let's have a look in accumulating in source registers. If you consider this simple addition, A equals A plus B, in a, let's say, regular form of an instruction, you can say add A, B. So add A and B and store the result in A. It means you have an opcode, a destination register, and 2 source registers. But it's quite obvious that the destination and one of the source registers are the same. So why should we store it in the program memory twice? We can have a special variant, an accumulating or as we call it, an in-place update variant. Add update AB, in which case the first source register is special as the result will be stored back to there. So here we saved one argument in the binary representation. And since this kind of possibility where updating, in-place update is possible, we can save a quite considerable amount of program memory. The other type of the other special variant of instructions is working with immediate values. So now if you consider A equals A plus 42, then if we have just a regular add additional instruction, like in the previous example, add AAB, then it means that 42 should be in a register. So you have a special operation, move 42 into register B, and then you can use the addition. In this case, you use actually 2 instructions to implement this, this behavior. If you have a special variant, add immediate value, then you can just use directly the immediate value instead of the second source register. So you saved binary space again. And of course you can combine these two way of handling arguments. So the combined special variant is add in place an immediate value, where you just define the source and destination register as one register and the immediate value to add to it. So here we saved even more program memory space. In ISL we have this kind of special variant basically for all similar instructions where it's possible to have. Okay. And then optimizing binary representation. So the things on the previous slide already contribute to having a reduced binary size in the program memory. But also it's important to be clever when you design the binary encoding of an instruction set architecture. So we want to have a high code density, which means that a particular piece of software should consume as small program memory as possible. But we have a lot of instructions in ISL. So to reach our goal, we must have variable length instructions. Our instruction, length of our instructions varies between 1 and 10 bytes, and here you can see the distribution. So most of them is 3 bytes long. The average is somewhere around 3.4 bytes. I don't want to go into much details about how the actual binary encoding is structured, but I would like to give you some idea what kind of problems or what kind of characteristics you need to think about. As I already mentioned, we want to maximize code density. So most typically, the more frequent instructions should have shorter representation. So the repeating instructions will consume less space. Then we also want to optimize the footprint of the microcode implementation itself. We want to be able to reuse codes for part of the code logic. So we, of course, want to have some regularity how we encode the operations. And also we want to be able to optimize not just the code, but the but the computation logic by sharing these parts also between similar instructions, grouping them together. And that's partially related to the third consideration is, of course, at the end, performance matters. So we want to minimize the actual execution time as well. Here, the binary encoding is relevant because decoding is dependent on the binary encoding. So with the clever spacing and formatting of the encoding types or the encoding formats, we can reduce the decode time, and also we can make possible that decoding an instruction and actually starting to perform the operation can overlap. So in this way we can minimize the execution time. Okay, and I talked a lot about binary coding and code density. So we have some preliminary results with ISA-L about code density. Or actually this diagram will show the binary size. So in this case the smaller is better. We compiled the Texas Instruments suite benchmarks with LLVM and normalized the results to our ISA-L. And as you can see, basically ARM Cortex requires at least 35% more program memory, and x86 requires 80% more program memory to store the store the same TI suite benchmark applications. So our target, one of our targets was to have a very dense code representation, which we think we reached. And well, with these exciting results, I would like also to wrap up. So I talked about our core technology, the IMSIS gene processing technology, our operation-oriented hardware architecture, the processor core, then our firmware, which is based on microcode and implements the actual instruction set architecture, which we tailor-made for LLVM assembly. I also talked about what is the relation and how we use an LLVM backend to efficiently and I can say simply target efficient or generate efficient code for ISA-L. And I also would like to mention that ISA-L, the implementation of the instruction set architecture itself and the software ecosystem around it, is still work in progress. So it's not available yet, but we plan to release it as an upgrade for our IMSIS EMBLA device sometime in the next year. So thanks for your attention, and I'm ready for questions. Yes, please. Yeah.
So where can I check the microcode that you wrote?
Sorry?
I want to check the microcode you wrote.
You want to check the microcode?
Yeah.
Well, we can discuss that offline if you really want to have a look into our microcode. So that's not open right now. So it's really connected to the hardware architecture, of course, and that's a proprietary thing. But if you are interested, we can take it offline.
So you can replace the very well-known and checked thing that is a part of LLVM and replace it with closed source microcode that we are not able to check. It's fine at all.
No, I can. Maybe I can answer this question by showing another slide. So right now we develop the microcode by hand, and right now with the not ISA-L microcode is not, in that sense, it's not released yet in any way, not as binary, not as source code. But previously the practice was that the company developed the microcode, and yes, it was proprietary and closed software or microcode firmware. With ISA-L, I cannot tell you how it will be released, but we plan actually to use LLVM also, not just to target our instruction set architecture, but to generate microcode from high-level software code. And in that sense, of course, if we will have So in that case, the microcode itself will be generated by an open source software, and so this problem could be resolved with that. I mean, was it? Yeah, okay. Yes?
How did you find the trade-off in complexity? Because it seems like you've got a simplified backend.
Yes.
Haven't you replaced part of that backend by something written in assembly?
Yes, so you are thinking about that the complexity from the backend was actually moved down to the microcode implementation, right? Well, yes, that's true. And of course, it means that, yes, the microcode needs to implement some complex features, which could be error prone, and it needs discipline to implement correctly. So actually, that's why we want to replace this, let's say, handcrafted microcode development with actually generating microcode. But also, this slide might be related. So our strategy is not implementing ISL at once, so because that would be quite big work. So in the first phase where we are now, we identify the base subset of the instruction set, and we implement that in microcode as a proof of concept, and it will be fully functional. Of course, it will not immediately provide the same code density because we will not be able to utilize all the instructions. But after that, and we partly started this work also, we want to implement an emulation support. So complex ISL instructions as a first step and as a reference implementation could be actually implemented using ISL itself, using the simpler already microcoded operations. And then later we plan to do continuous development to actually on demand support the features which actual customers need or the community needs. Was it answered to your question? Okay, thank you. Yes?
So, can you explain why you want to do this? Because, right, so basically you're constructing your ISA based on LLVM to simplify how you write the backend for it. But
That's just...
you had to do this, I mean, there were some...
Okay.
What kind of constraint you had that forced you to do this instead of choosing like a MIPS or ARM or whatever other...
Okay. So I think your question, I tried to rephrase it. So one part of your question was why do we need to, okay, sorry. So you asked what are the benefits of using microcode to implement this ISL, special instruction set architecture. And then you also asked about, why using this processor. It's somewhat related, but I would like to take it as two parts. So the first part would be, sorry, I just want to find the slide. So of course, having a simple way to implement a backend is good. It's good for IMSIS because IMSIS is a processor company, and we have expertise with the processor and microcode development. So implementing complex compilers is not really our field. So if we can have a simple backend, that's just good. But actually, that's just a side product. What we wanted to utilize microcode for are these 5 characteristics. So in general, we believe that by matching LLVM, the LLVM assembly level, we can have a rich instruction set which provides complex instructions. So the binary code, the size required in the program memory for the executable code can be minimized, smaller than other mainstream architectures. So that's a benefit. And also, we believe that this microcoding the complex operations helps improving the performance. So in this case, the whole complex operation is in microcode, and otherwise, if we would have only a simple RISC instruction set, then the same operation would take, I don't know, a sequence of assembly instructions, which would take extra time to decode all of the instructions and so on and so forth. Yes, And then why not using other processors in general? Well, because we have our own processor technology, and yeah, of course we want to exploit the possibilities in that.
I was wondering what was the drawback, or why it was better to design your own compared to using something that...
Yes, and then, sorry, it's better to select directly. So this is a bit more detailed overview of what we support. What is interesting is these green things. So we have the Java support, we have ISL, and we plan to have a special part of the instruction set support, DSIX. This is domain-specific instruction extensions. So as I said, microcoding provides us flexibility and reconfigurability also, and we plan to generate microcode from hotspots of application code also. So it means that not just ISL, the general purpose ISL itself, can be utilized and exploit the processor core, but we can also implement complex application-specific features in microcode to improve the performance.
Okay.
So that's also a special feature. Okay. Yes, please.
You made some claims about how your ISR compares in terms of code density to existing ones. These claims look very similar to the claims made yesterday in the RISC-V talk. So how does your ISR compare to RISC-V in code density?
Yes, that's a good question. So we didn't compare with RISC-V, and probably that's a missing thing, which we should do. But we believe that RISC-V is still a RISC architecture. So we were, of course, relates back to the previous question. So why we decided to implement something specific for LLVM, and yeah, RISC-V is there. But we believe that our binary coding matching the LLVM assembly instruction set provides better code density. I cannot tell you right now actual figures, but we will check that out. So, yes. Is that answer? Okay. Yes? Yes? Do you want? Yes, you're in the black shirt. Yeah. Oh, sorry. Yeah.
I was wondering, do you have any benchmarks on the performance?
Not.
Here?
Mm-hmm.
And similar question to that one. This looks to me like you're looking for more complex operations to be done on the hardware side. So this looks like there were a couple of attempts to, for instance, to have, for instance, JavaScript interpreter or Java code interpreters, bytecode developed on the hardware side itself. So do you have any ideas going in that way, so you could implement these opcodes like your own instructions and maybe
I see.
is there?
Yes. So about interpreting different things, of course, microcode. So this is not hardware implementation. Yeah, it's similar, very low level, and it's very close to the hardware. But yeah, microcode is rather software than hardware if I need to compare. And of course, it's possible to implement other instruction sets, other kind of operations in microcode. Right now, we don't have any plans to do it, but it would be a possibility if we see that there is a customer need or something for that.
But if you're emulating all of these instructions, so you're getting the real benefit out of that rather than generating efficient RISC code or such. So that's my...
Okay, I see. So you are rather thinking about directly executing some special instruction set or just compiling it into some good instruction set architecture, or so that's
would that be a basis for some future ISOs from you implemented in hardware, or your plan is just to emulate that from now on and work on that basis?
Okay, so your idea is to have this microcode implementation as a reference and then move everything into hardware?
Yeah.
Okay, so no, we are not planning to do that, no. So we believe that microcode itself is, it provides us the flexibility to be able to change, to be able to, maybe I show another slide then. So as I mentioned, our core.
But are you getting some benchmark results?
Oh yes, your first question. Sorry, yes, the performance. So as I said, the ISL implementation is still work in progress. So we couldn't really execute anything yet, but we are close. So I cannot tell you any actual execution time figures. But we expect that we can be better than ARM Cortex-M0, for example. But I don't have any figures yet. So that part is work in progress. So I can tell you about our estimates, but yeah, that's nothing. But about keeping everything in microcode and not moving into hardware, as I mentioned, our processor core is quite small compared to the mainstream ones. And it's theoretically possible. Well, we have 65 nanometer, what we use now, and we don't have this really massively multi-core solution yet. But it's theoretically possible actually to have several thousands of cores on state-of-the-art processing nodes. And in this case, each processor core has its own microprogram, and it's software configurable. So depending on the application, the software itself would be able to, let's say, dynamically reconfigure, repurpose each one of the cores separately, depending on the actual application requirements. So if we would put something into hardware, then of course this wouldn't be possible, everything would be fixed. So this kind of flexibility, we believe that will be very important in the future. That's why we want to keep everything in microcode. All right, so I hope that answered your question, and we can take that offline, okay? So thank you for your attention again.